Stone does not forget. It does not exaggerate. It does not revise its testimony to please a committee or protect a reputation. Stone simply records what happened to it, faithfully, patiently, in a language that takes years of training to read but that, once read, cannot be argued away. And the stone of the Great Sphinx of Giza is saying something that a significant portion of the academic world does not want to hear. On the western bank of the Nile, on a limestone plateau overlooking the floodplain that has sustained human life for millennia beyond reckoning, there sits a monument carved from the living bedrock. It is 73 meters long. It is 20 meters tall. It weighs an estimated 200,000 tons. It is the largest monolithic sculpture on the face of the earth, and the erosion on its body does not match the erosion on any other structure from the era in which it is supposed to have been built. Not approximately, not roughly, not with minor discrepancies that can be waved away with a footnote. The erosion is different in kind, different in pattern, different in depth, different in character, and the difference tells a story that, if true, would force us to rewrite not just the history of Egypt, but the history of civilization itself. The conventional date for the Sphinx is around 2500 before the Common Era. That places it in the 4th dynasty of ancient Egypt, during the reign of the pharaoh Khafre, whose pyramid rises behind it on the Giza Plateau. In this reading, the Sphinx is roughly 4,500 years old. It is ancient, it is impressive, but it is comprehensible. It fits within a framework that scholars have spent more than a century constructing, a framework in which civilization begins in Mesopotamia and Egypt around 3000 to 3500 before the Common Era, and in which everything before that date is prehistory, a time of small villages, simple tools, and modest ambitions. The Sphinx in this framework is the product of one of the first great civilizations, remarkable but not mysterious, extraordinary but not impossible, old but not too old. But the erosion patterns tell a different story. They tell a story of water, not the trickle of occasional desert rain, not the slow creep of groundwater through porous limestone, not the corrosive action of wind-driven sand, water, heavy, sustained, prolonged rainfall, cascading down the walls of the Sphinx enclosure, cutting deep vertical channels into the limestone, dissolving the calcium carbonate matrix, and sculpting the rock into smooth, undulating, flowing forms that are utterly unlike the angular, horizontally banded erosion produced by wind and sand on every other structure of comparable age on the Giza Plateau. The kind of rainfall that has not fallen on the Giza Plateau in anything like the quantities required for at least 5,000 years before the Sphinx is supposed to have been carved. Perhaps much longer, perhaps 7,000 years, perhaps 8, perhaps more. If the erosion patterns are telling the truth, then the Sphinx was not built 4,500 years ago. It was built at a time when heavy rain still fell on the Giza Plateau, during a climatic period known as the African Humid Period, or the Neolithic Subpluvial, when the Sahara was not a desert, but a green savanna dotted with lakes, rivers, and grasslands. That period ended, gradually but decisively, between 7,000 and 5,000 years before the present. If the Sphinx was carved while those rains were still falling, it could be 7,000 years old, it could be 9,000 years old. At the outer edge of the estimates, it could be older still. And at any of those ages, it predates everything we think we know about the origins of civilization. It predates writing, it predates the wheel, it predates the first cities, it predates agriculture in Egypt. It predates the entire framework within which mainstream archaeology understands the human past. That is the claim. That is what the stones are saying. And for more than 3 decades, the academic world has been trying to find a way to make them stop. The resistance has not been casual. It has not been the polite disagreement of scholars over a minor point of interpretation. It has been fierce, sometimes personal, and often dismissive. Geologists have been told they are not qualified to comment on archaeological matters. Independent researchers have been denied access to the monument. Careers have been threatened. Papers have been rejected. And through it all, the erosion has remained unchanged, unhurried, indifferent to the passions of the creatures who scramble around the base of the monument arguing about what it means. The rocks do not care who wins the argument. They simply record what happened. And what happened, according to the physical evidence on the enclosure walls, involved water. A great deal of water, over a very long period of time, at a date that no mainstream Egyptologist is comfortable accepting. By the end of tonight, you are going to understand what those erosion patterns actually look like, how they differ from the erosion on every other ancient structure at Giza, and why the distinction matters. You are going to learn the names of the geologists, the archaeologists, and the independent researchers who have examined the evidence, and you are going to hear what each of them concluded and why. You are going to walk through the counter-arguments, the alternative explanations, and the institutional dynamics that have kept this debate simmering for over 30 years without resolution. And you are going to confront a question that no comfortable answer can satisfy. What if the monument we thought we understood is actually a relic of a world we have not yet discovered? Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand what the erosion patterns on the Sphinx are telling us, we first need to understand the science of how rock erodes. This is not a casual topic. It is not something that can be understood through intuition or common sense alone. Rock erosion is a complex geological process governed by the interaction of multiple variables, including the composition and porosity of the rock, the climate and weather conditions to which it is exposed, the presence or absence of groundwater, the chemical properties of any water that contacts the rock, the biological activity on and within the rock surface, and the duration of exposure. Different combinations of these variables produce different erosion profiles, different surface textures, and different patterns of degradation. And a trained geologist can read these patterns the way a doctor reads an X-ray, extracting information about the history of the rock from the physical evidence preserved in its surface. Limestone, the rock from which the Sphinx is carved, is a sedimentary stone composed primarily of calcium carbonate. It is formed from the accumulated remains of marine organisms, shells, coral, and microscopic creatures that lived in ancient seas, and whose remains were compressed over immense spans of time into solid rock. Limestone is relatively soft as stones go, rating between 3 and 4 on the Mohs scale of mineral hardness, which means it can be scratched by a steel knife. It is also porous, meaning it contains tiny spaces and channels through which water can penetrate. And it is chemically reactive, meaning it dissolves when exposed to acidic water, including the mildly acidic rainwater produced when carbon dioxide in the atmosphere combines with water vapor to form carbonic acid. These properties make limestone particularly susceptible to erosion by water and particularly responsive to changes in the amount, type, and duration of water exposure. There are, broadly speaking, 2 main types of erosion that affect exposed limestone surfaces. The first is mechanical erosion, also called physical erosion, in which particles of sand, dust, or other material are carried by wind or water and physically abrade the rock surface, wearing it away through friction. In a desert environment, the dominant form of mechanical erosion is aeolian erosion, erosion caused by wind-blown sand. Wind carries fine particles of sand at high velocity, and these particles strike exposed rock surfaces like tiny projectiles, gradually wearing away the softer areas while leaving the harder areas relatively intact. Over time, this process produces a characteristic erosion profile. The softer layers of the limestone recede behind the harder layers, creating a stepped, horizontally banded pattern, like the pages of a book seen edge-on, with alternating ridges and hollows, corresponding to the alternating hard and soft layers of the stone. The surface texture is rough and angular, with sharp edges and jagged projections where hard nodules or resistant layers protrude from the softer matrix. This is the erosion pattern you see on virtually every exposed limestone surface in the Egyptian desert. It is the pattern you see on the Old Kingdom tombs cut into the cliffs and plateau surface at Giza. It is the pattern you see on the walls of the quarries from which the pyramid blocks were extracted. It is, in short, the signature of 4,500 years of desert weathering. The second type of erosion is chemical erosion, also called dissolution or solution weathering, in which water reacts chemically with the calcium carbonate in the limestone and dissolves it. When rainwater falls on a limestone surface, it penetrates the pore spaces and begins dissolving the calcium carbonate matrix from within. As the water flows down a vertical surface, it dissolves the rock preferentially along the pathways where flow is concentrated, creating vertical channels, grooves, and rounded depressions. Over time, these channels deepen and widen, producing a distinctive erosion profile that is qualitatively different from the profile produced by wind erosion. Instead of horizontal bands, the surface shows vertical channels. Instead of angular, sharp-edged projections, the surface is smooth and rounded. Instead of a stepped profile with hard layers protruding, the surface is flowing and undulating, with the hard and soft layers eroded to roughly the same depth, because water dissolves both types of rock, though at different rates. The overall effect is organic, sinuous, almost liquid in appearance, as if the rock itself had melted and refrozen in a new shape. This type of erosion is seen all over the world in regions that receive significant rainfall. The karst landscapes of Slovenia, the Yucatan Peninsula of Mexico, the limestone pavements of northern England, the tower karst of southeastern China, all of these display the characteristic features of precipitation-induced chemical weathering on limestone. The features are well documented, well understood, and unambiguous to any geologist trained to recognize them. They include dissolution channels, also called cairn or lapies, which are narrow, vertical grooves cut into the rock surface by flowing water. They include solution flutes, which are wider, shallower channels with rounded cross-sections. They include rounded dome-shaped residual features where the rock between the channels has been smoothed by sheet flow. And they include a general softening and rounding of all sharp edges and angular features, because water attacks all surfaces, not just the soft ones. Now here is the crucial point. The walls of the Sphinx enclosure, the U-shaped trench cut into the bedrock of the Giza Plateau around the body of the Sphinx, display features that are consistent with precipitation-induced chemical weathering. They display deep, vertical channels. They display rounded, undulating surfaces. They display a flowing, organic profile in which the hard and soft layers have been eroded to roughly the same depth. And they do not display the angular, horizontally banded profile that would be expected from 4,500 years of wind and sand erosion in a desert environment. This is the observation that launched the entire debate. This is the foundation upon which every subsequent argument, analysis, and counter-argument has been built. The observation was not made by an Egyptologist. It was not made by an archaeologist. It was first noted, in passing, by the Alsatian philosopher and symbolist René Schwaller de Lubitsch in his 1957 work on the Temple of Luxor. Schwaller observed that the erosion on the body of the Sphinx appeared to have been caused by water rather than by wind and sand. He did not pursue the observation. He did not investigate its implications. He mentioned it as an aside, a footnote in a much larger philosophical argument about the nature of ancient Egyptian knowledge. But the observation was picked up decades later by an American writer named John Anthony West, who recognized its revolutionary potential and set out to find a geologist who could evaluate it rigorously. That geologist was Robert Schoch, and his evaluation changed everything. Robert Schoch held a doctorate in geology and geophysics from Yale University. At the time West approached him, in the late 1980s, he was a faculty member at Boston University, specializing in stratigraphy and sedimentary geology. His credentials were impeccable, his expertise was directly relevant, and his initial reaction to West's claim was skepticism. Extraordinary claims require extraordinary evidence, and the claim that the Sphinx might be thousands of years older than the conventional date was about as extraordinary as archaeological claims get. It is worth pausing here to consider the magnitude of the question that Schoch was being asked to investigate. The Sphinx is not merely an archaeological curiosity. It is one of the most iconic monuments in the history of human civilization. It has been visited, described, depicted, and wondered at by travelers, scholars, and artists for thousands of years. Pliny the Elder mentioned it in his Natural History. Arab writers of the medieval period speculated about its purpose and its age. Napoleon's soldiers, during the French campaign in Egypt in 1798, reportedly stared at it in silent amazement, though the popular story that Napoleon's troops shot off the Sphinx's nose is almost certainly false, as sketches from before the French expedition show the nose already missing. The Danish naval captain Frederick Louis Norden depicted the Sphinx in drawings published in 1755, clearly showing the nose already absent. The question of who damaged the nose has its own long history, with various candidates proposed, including the medieval Sufi iconoclast Saim al-Dar, who is said to have defaced it in the 14th century of the Common Era. Throughout all of these centuries of observation, no one had questioned the basic assumption that the Sphinx was the product of the Old Kingdom pharaohs. The association with Khafre was established in the 19th century by Mariette and others, and it was accepted without serious challenge for more than 100 years. To suggest otherwise was to challenge not just a specific date, but an entire edifice of scholarship built over generations. The careers of hundreds of Egyptologists, the contents of thousands of textbooks, the narratives of countless museum exhibitions, all rested on the assumption that the Sphinx was 4th dynasty. Overturning that assumption would require not just good evidence, but exceptional evidence. And Schoch knew this. Schoch agreed to examine the Sphinx in person. He travelled to Egypt in 1990 and conducted a preliminary survey of the monument and its enclosure. He returned in 1991 with a team that included the geophysicist Thomas Dobecki, who brought seismic refraction equipment to measure the depth of subsurface weathering in the bedrock beneath and around the Sphinx. What they found confirmed Schwaller's observation and added new dimensions to it. The visual evidence was striking. The walls of the Sphinx enclosure, particularly the upper portions and the western end, displayed the classic features of precipitation-induced weathering. Deep vertical channels, some extending more than a meter into the rock, ran from the top of the enclosure walls to the bottom. The surfaces between the channels were rounded and smoothed, not angular and rough. The hard and soft layers of the limestone had been eroded to roughly similar depths, producing a flowing, undulating profile rather than a stepped one. Schoch compared these features to the erosion on the nearby Old Kingdom tombs, rock-cut structures from the same plateau that are firmly dated to the 4th, 5th, and 6th dynasties. The contrast was dramatic. The tomb walls displayed the classic Aeolian erosion profile, angular, horizontally banded, with the soft layers receding behind the hard layers. The Sphinx enclosure walls displayed a completely different profile. The two types of erosion were not subtly different. They were qualitatively distinct, as different as the handwriting of two different people. But Schoch did not stop at visual observation. The seismic refraction data provided an additional dimension of evidence. Seismic refraction is a technique in which a small charge or mechanical impact generates sound waves that travel through the rock. The speed at which these waves travel depends on the density and integrity of the rock. Weathered rock, which has been weakened by chemical dissolution or mechanical abrasion, transmits sound more slowly than intact rock. By measuring the velocity of seismic waves at different locations around the Sphinx enclosure, Schoch and Dobecki could estimate the depth of the weathered zone, the layer of degraded rock between the surface and the intact bedrock beneath. The results were significant. The seismic surveys showed that the weathered zone on the western wall of the Sphinx enclosure, the rear of the monument, was substantially deeper than the weathered zone on the southern wall near the front. If the entire enclosure had been carved at the same time, as the conventional model assumes, the depth of weathering should be roughly uniform throughout, because all surfaces would have been exposed to the same environmental conditions for the same duration. The differential weathering depth suggested that the western wall had been exposed for a significantly longer period than the southern wall, implying that the enclosure was carved in phases, with the western end being carved first and the eastern end being extended at a later date. This finding had profound implications. If the rear of the Sphinx enclosure was carved substantially earlier than the front, then the conventional model, which attributes the entire monument to a single construction phase during Khafre's reign, was incomplete at best. The earlier phase, represented by the more deeply weathered western end, could predate the Fourth Dynasty by centuries or even millennia. And if the earlier phase was carved during a period of significant rainfall, the depth of the weathering became a rough clock, measuring the accumulated effects of water erosion over the intervening millennia and pointing toward a construction date far earlier than 2500 before the Common Era. To appreciate the scale of this claim, consider the climate history of the Giza region. The Giza Plateau sits at roughly 30 degrees north latitude on the eastern edge of the Sahara Desert. Today, it receives an average annual rainfall of approximately 25 millimeters, less than 1 inch. It is one of the driest inhabited regions on Earth, but it was not always. During the African humid period, which is generally dated from roughly 11,700 to roughly 5,500 years before the present, the climate of North Africa was dramatically wetter. Monsoon rains, driven by changes in the Earth's orbital parameters that shifted the intertropical convergence zone northward, penetrated deep into what is now the Sahara, transforming it from a hyperarid desert into a mosaic of grasslands, savannas, lakes, and wetlands. The evidence for this transformation is overwhelming. Lake sediment cores, pollen records, cave formations, and the remains of aquatic animals in the heart of the modern desert all confirm that the Sahara experienced a prolonged wet phase that supported not only vegetation but also large human populations engaged in herding, fishing, and early cultivation. The rainfall during the African humid period was not uniform across the entire Sahara. It varied by region, by elevation, and by latitude. In the Giza region, the rainfall was almost certainly less than in the central Sahara, which received the full force of the monsoon, but it was substantially more than the virtually negligible rainfall that the region receives today. Estimates vary, but many paleoclimatologists suggest that the Giza region during the height of the humid period may have received somewhere between 100 and 200 millimeters of annual rainfall, perhaps more, enough to support grassland vegetation and seasonal streams. The transition from the humid period to the current arid conditions was not sudden. It was a gradual process that unfolded over roughly 2,000 years, from approximately 5,500 to 3,500 years before the present. During this transitional period, rainfall gradually decreased, vegetation retreated, lakes shrank and disappeared, and the desert advanced. By 3000 before the Common Era, approximately the beginning of the dynastic period in Egypt, the climate of the Giza region was essentially arid, similar to what it is today. By the time of Khafre, around 2500 before the Common Era, the region had been effectively dry for 500 to 1,000 years. This climate timeline is critical to the erosion debate. If the vertical, rounded, precipitation-style erosion on the Sphinx enclosure walls was caused by rainfall, then that rainfall must have occurred while the enclosure walls were exposed. And if the last period of significant rainfall on the Giza Plateau ended at least 5,000 years ago, and possibly as early as 7,000 years ago, then the enclosure walls must have been carved before that rainfall ended. This pushes the construction date of the Sphinx back to at least 5,000 before the Common Era, and potentially much earlier. Let that sink in. 5,000 before the Common Era is roughly 7,000 years ago. That is 2,500 years before the conventional date. It is 1,500 years before the beginning of the First Dynasty. It falls within the pre-dynastic Naqada I period, when the inhabitants of the Nile Valley, so far as the current archaeological record indicates, were living in small farming villages and burying their dead in simple graves with modest offerings of pottery and flint tools. There is no evidence, within the currently known pre-dynastic record, of a society capable of monumental stone carving on the scale of the Sphinx. And 7,000 before the Common Era, the more expansive estimate, takes us back 9,000 years to a period when the Nile Valley was inhabited by early Neolithic communities whose archaeological footprint is barely visible. The question is inescapable. If the erosion patterns are telling the truth, then who carved the Sphinx? Not Khafre, not any pharaoh of the Old Kingdom, not any culture that the existing archaeological record can identify. Someone else, someone we have not found. someone whose existence, if real, would transform our understanding of the deep human past. But here is the problem. Extraordinary claims require extraordinary evidence. And the question of whether the erosion patterns on the Sphinx enclosure really do indicate rainfall weathering, or whether they can be explained by other mechanisms operating within the conventional timeframe, has been the subject of intense and sometimes bitter debate for over 3 decades. The evidence has been examined, challenged, defended, reinterpreted, and argued over by geologists, archaeologists, Egyptologists, climatologists, and engineers, with strikingly different conclusions. To understand the debate, we need to go deeper into the evidence, much deeper. But before we do, it is worth establishing the full physical context of the Sphinx and its enclosure, because the details matter. The Sphinx enclosure is not simply a hole in the ground. It is a carefully shaped excavation in the bedrock of the Giza Plateau, a U-shaped trench that follows the contours of the Sphinx's body. The walls of the enclosure rise to heights of between 5 and 10 meters above the enclosure floor, depending on the location, and they expose a cross-section of the geological layers that make up the plateau. These layers are not uniform. They vary in hardness, porosity, color, and chemical composition. The softest layers, composed of relatively pure calcium carbonate, with a high proportion of clay minerals and fossil fragments, are the most susceptible to erosion. The hardest layers, composed of dense, crystalline limestone with fewer impurities, are the most resistant. The alternation of hard and soft layers produces, under wind erosion, the characteristic stepped profile mentioned earlier, with hard layers protruding and soft layers receding. The Sphinx itself is carved from 3 distinct geological members. The lowest member, forming the base and the floor of the enclosure, is a hard, dense limestone that provides a solid foundation. The middle member, forming the bulk of the body, is a softer, more porous limestone that has suffered the most severe erosion. This is the layer where the vertical channels, the rounded profiles, and the flowing surfaces that are at the center of the controversy are most pronounced. The upper member, forming the head, is a harder limestone that has resisted erosion more effectively, which is one reason the head is in better condition than the body, though as we shall discuss later, this may not be the only reason. The enclosure itself has had a complex history of exposure and burial. For most of the past 2 millennia, the Sphinx was buried up to its shoulders, or even its neck in wind-blown sand. Periodic clearing operations, some documented in ancient inscriptions, temporarily exposed the body before the sand returned. The Dream Stela of Thutmose IV, dating to the New Kingdom, records one such clearing operation in the 14th century before the Common Era. The Roman Emperor Marcus Aurelius may have ordered another clearing during the 2nd century of the Common Era, and in the modern period Giovanni Battista Caviglia partially cleared the Sphinx in 1817, followed by Auguste Mariette in the 1850s, and finally by Émile Barrès, whose comprehensive excavation between 1925 and 1936 fully exposed the body for the first time in the modern era. Each period of burial and re-exposure has affected the condition of the monument. Sand burial protects the stone from wind erosion but traps moisture against the surface, promoting chemical weathering and salt crystallization. Re-exposure subjects the stone to the drying effects of sun and wind, causing salt crystals within the pore spaces to expand and contract, further weakening the rock. This cycle of wetting and drying, exposure and burial has undoubtedly contributed to the deterioration of the Sphinx. But the question at the heart of the debate is whether these processes, operating over 4,500 years in an arid climate, are sufficient to explain the specific erosion features visible on the enclosure walls, or whether an additional factor, sustained rainfall from a wetter climatic period, is required. The distinction is crucial. It is not a matter of more erosion versus less erosion. It is a matter of different types of erosion producing different physical features. Wind erosion produces angular, horizontal features. Salt weathering produces flaking, granular disintegration, and preferential attack on soft layers. Water erosion from rainfall produces vertical channels, rounded surfaces, and roughly uniform erosion across hard and soft layers. These are different processes with different signatures, and the Sphinx enclosure walls display the signature of water erosion, not the signature of wind or salt. Then something happened that changed everything. In October of 1991, Robert Schoch presented his findings at the annual meeting of the Geological Society of America in San Diego. The paper he delivered, co-authored with John Anthony West, argued that the erosion profiles on the walls of the Sphinx enclosure were inconsistent with the conventional 4th Dynasty construction date, and instead indicated a period of prolonged rainfall exposure that had not occurred on the Giza Plateau for thousands of years before Khafre's reign. The paper proposed a minimum construction date of approximately 5,000 before the Common Era, and a possible date as early as 7,000 before the Common Era. The reaction was swift and divided. Among the geologists present, the response was cautiously interested. Schoch was presenting geological evidence using standard geological methods, and his observations about the difference between the Sphinx enclosure erosion and the erosion on nearby Old Kingdom tombs were empirically grounded. The data could be checked. The observations could be verified. The methodology was transparent. Whatever conclusions one might draw from the evidence itself was real. Among the Egyptologists, the reaction was very different. The claims struck at the foundations of the established chronological framework. If the Sphinx was thousands of years older than the conventional date, it meant that a complex, organized society capable of monumental stone carving had existed in the Nile Valley long before the earliest known civilization. This contradicted nearly everything that mainstream archaeology believed about the development of human societies. It suggested that the neat, linear progression from hunter-gatherer to farmer to villager to city dweller, the standard model of civilizational development, was either wrong or radically incomplete. The implications were so vast, so disruptive, that many scholars simply refused to engage with them. The most prominent critic was Mark Lehner, an American Egyptologist who had spent decades studying the Giza Plateau and who is widely regarded as the world's leading authority on the Sphinx. Lehner had personally mapped the Sphinx and its enclosure in extraordinary detail. He had excavated the workers' settlements south of the pyramids, uncovering the bakeries, dormitories, and administrative buildings that housed and fed the labor force that built the Giza complex. His knowledge of the plateau was unmatched, and his assessment of Schoch's claims was unequivocal. The Sphinx, he maintained, was built by Khafre. The geological evidence did not require an earlier date. The erosion could be explained by other factors. Lehner's primary counter-argument focused on what he called the chemical weathering model. He argued that the rounded and undulating erosion on the Sphinx enclosure walls was not the result of rainfall running down the walls from above, as Schoch contended, but rather the result of moisture migrating through the porous limestone from the saturated zone below. The Giza Plateau sits above a water table that has fluctuated significantly over the millennia. During periods of high water table, moisture is drawn upward through the limestone by capillary action. As this moisture reaches the surface and evaporates, it deposits salts, primarily sodium chloride and calcium sulfate, within the pore spaces of the rock. These salt crystals grow over time, exerting pressure on the surrounding rock matrix and gradually breaking it apart from the inside. This process, known as salt weathering or haloclasty, is well documented in arid environments and can produce significant surface degradation over thousands of years. Lehner argued that salt weathering, combined with occasional rainfall and the unique microclimate created by the enclosed Sphinx trench, could account for the observed erosion without invoking a construction date earlier than the 4th Dynasty. The Sphinx enclosure, being a deep sheltered trench cut into the plateau, would trap moisture, shade its walls from direct sunlight, and create conditions conducive to condensation and chemical attack that would not apply to the open, exposed surfaces of the nearby tombs. This microclimate effect, Lehner suggested, explained why the Sphinx enclosure showed different erosion from the tombs, not because it was carved at a different time, but because it was carved in a different shape, a shape that created its own distinctive weathering environment. This is a serious argument. It deserves careful consideration, and it has been carefully considered by Schoch and by other geologists over the 3 decades since it was first proposed. The responses have been detailed and technical, and they illuminate the core difficulty of the debate. The first problem with the salt weathering explanation is that it does not easily account for the specific shape of the erosion features on the Sphinx enclosure walls. Salt weathering, as documented in geological literature, tends to attack the softer, more porous layers of limestone preferentially, because these layers absorb more moisture and provide more pore space for salt crystal growth. The result is a stepped, horizontally banded erosion profile, with the softer layers receding behind the harder layers, exactly the profile that is seen on the Old Kingdom tombs and other exposed limestone surfaces on the Giza Plateau. But the Sphinx enclosure walls do not show this profile. They show a profile in which the hard and soft layers have been eroded to roughly the same depth, producing a smooth, undulating surface rather than a stepped one. This is the signature of water flowing down a vertical surface, which dissolves both hard and soft layers, not the signature of salt crystallization, which preferentially attacks the soft layers. The second problem is the depth and orientation of the erosion channels. The deepest channels on the Sphinx enclosure walls run vertically, from top to bottom. They are consistent with water flowing downward under gravity, cutting preferential pathways through the limestone as it flows. Salt weathering does not produce vertical channels of this type. Salt damage tends to produce horizontal or irregular patterns of surface flaking and granular disintegration, not deep, linear, vertically oriented grooves. The vertical channels on the Sphinx enclosure walls are, in the judgment of Schoch and several other geologists who have examined them, diagnostic of water erosion from precipitation. The third problem is the comparison with the nearby tombs. Lina's microclimate argument proposes that the enclosed shape of the Sphinx trench created conditions different from the open tomb facades, and that this difference accounts for the different erosion profiles. But this argument would predict that other enclosed rock-cut structures on the plateau, such as the deep quarries and the shaft tombs that descend vertically into the bedrock, would show similar rounded erosion. They do not. The quarries and shaft tombs of the Old Kingdom show the same angular, horizontally banded erosion as the open tomb facades, despite being enclosed spaces that would presumably experience similar microclimate effects. This observation weakens the microclimate hypothesis considerably. If enclosed spaces routinely produced rounded erosion through moisture trapping and salt weathering, we would expect to see rounded erosion in every enclosed rock-cut space on the plateau. We do not, and it gets worse. The argument from the seismic data compounds the problem. If the differential weathering depth between the western and eastern ends of the Sphinx enclosure was simply the result of variations in salt weathering intensity, or variations in the microclimate within different parts of the enclosure, there is no obvious reason why the western end would be consistently and substantially more deeply weathered than the eastern end. The microclimate of a U-shaped trench does not vary dramatically from one end to the other. The salt content of the groundwater does not change significantly over a distance of 70 meters. The most parsimonious explanation for the differential weathering depth is that the western end has been exposed for a longer period of time, and that implies phased construction, with the rear of the Sphinx enclosure being carved significantly earlier than the front. There is a fourth objection that is less often discussed but equally important. The erosion on the Sphinx enclosure walls extends to a considerable depth below the modern surface. The lower portions of the walls, down to the floor of the enclosure, show extensive weathering that is consistent with prolonged water exposure. If the Sphinx enclosure had been buried in sand for most of its history, as is known to be the case, the lower portions of the walls would have been protected from wind erosion and, to some extent, from salt weathering. Yet they are deeply eroded. The most straightforward explanation for deep erosion on surfaces that were buried for much of their history is that the erosion occurred before the burial during a period when the walls were exposed and subject to rainfall. and that period by climatic reckoning must have ended thousands of years before the conventional construction date. The geologist Colin Reeder, working independently in the late 1990s, reached conclusions that partially corroborated shock while proposing a more conservative timeline. Reeder, a British geologist and engineer with no prior connection to either shock or West, conducted his own examination of the Sphinx enclosure and agreed that the erosion patterns were inconsistent with a 4th dynasty construction date. However, Reeder proposed that the Sphinx might date to the early dynastic period or the late pre-dynastic, roughly 3000 to 3500 before the Common Era, rather than the much earlier dates suggested by shock. Reeder argued that the rainfall during the late pre-dynastic and early dynastic periods, while significantly less than during the peak of the humid period, might have been sufficient to produce the observed erosion on freshly carved limestone surfaces, which would be more susceptible to chemical weathering than already weathered surfaces. Reeder's work is important for several reasons. First, it demonstrates that the geological evidence for water erosion on the Sphinx enclosure is not a fringe interpretation promoted by a single maverick geologist. A second qualified geologist, working independently, examined the same evidence and reached a similar conclusion. Second, Reeder's more conservative timeline addresses one of the most powerful objections to Shock's hypothesis: the absence of any known culture in the Nile Valley capable of monumental stone carving during the periods Shock proposes. Reeder's dates place the Sphinx in a period when social complexity in the Nile Valley was rapidly increasing, when regional chiefdoms were consolidating power, and when the organizational capacity for ambitious construction projects may have been developing, even if the surviving archaeological evidence does not yet attest to monuments on the scale of the Sphinx. But Reeder's work also raises its own problems. If the Sphinx was carved in the late pre-dynastic or early dynastic period, it still predates the conventional date by at least 500 to 1,000 years. It still falls outside the established chronological framework for the Giza complex, and it still implies a level of social organization and technical skill that the pre-dynastic archaeological record does not currently support. Reeder's hypothesis is less radical than Shock's, but it is still radical enough to challenge the mainstream narrative in fundamental ways. There is a further subtlety in the erosion evidence that is often overlooked in popular accounts of the debate, but that matters considerably to the specialists. The erosion on the Sphinx enclosure walls is not uniform in depth. The upper portions of the walls, which have been exposed to the atmosphere for the longest period, show the deepest erosion. The lower portions, which were buried under sand for much of the Sphinx's history, show less erosion. This vertical gradient in erosion depth is exactly what one would expect from rainfall weathering. Rain falls from above and runs down the walls under gravity. The upper portions of the walls receive the most direct exposure to rainfall and the highest concentration of flowing water. The lower portions receive less direct exposure, particularly if sand was already beginning to accumulate at the base of the walls during the rainfall period. The gradient is consistent with water flowing from top to bottom. It is not consistent with salt weathering from groundwater, which would attack the lower portions of the walls more severely, since they are closer to the water table. Shock has also drawn attention to the condition of the Sphinx temple, the structure built from blocks quarried from the Sphinx enclosure. The core blocks of this temple, the large limestone blocks that form its inner structure, show the same rounded, water-worn erosion as the Sphinx enclosure walls. This is significant because the temple blocks were cut from the enclosure walls and therefore preserve the same erosion features. But the temple also has an outer layer of granite-facing blocks, applied in a style consistent with 4th dynasty construction techniques. The granite facing appears to have been added to protect and renovate the already deteriorating limestone core. In other words, the core blocks were already eroded before the granite was applied. If the granite facing is 4th dynasty, then the core blocks and the enclosure from which they were quarried must be older than the 4th dynasty. This observation is one of the most underappreciated pieces of evidence in the entire debate. It is not based on subjective interpretation of erosion profiles. It is based on a straightforward physical observation. The granite facing was applied over limestone blocks that were already eroded. The granite facing is 4th dynasty. Therefore, the limestone erosion predates the 4th dynasty. The logic is simple, almost inescapable, and yet it has received far less attention than the more dramatic claims about the Sphinx's potential age. There is also the question of what the ancient Egyptians themselves thought about the Sphinx. The earliest known name for the Sphinx in Egyptian texts is Horemakhet, meaning Horus of the horizon. This name first appears in the New Kingdom period, around 1300 before the Common Era, more than 1,000 years after the Sphinx's conventional construction date. Before the New Kingdom, there are no known textual references to the Sphinx at all. This silence is puzzling. If the Sphinx was built by Khafre, one of the most powerful pharaohs of the Old Kingdom, why is there no Old Kingdom text that mentions it? Why is there no Middle Kingdom text that mentions it? Why does the monument apparently disappear from the written record for more than 1,000 years after its supposed construction, only to reappear in the New Kingdom under a name, Horemakhet, that associates it with the sun god rather than with any specific pharaoh? One possible explanation is that the Sphinx was so well known, so familiar, so much a part of the landscape, that no one felt the need to mention it in writing. This is possible, but it is not very satisfying, given the Egyptian penchant for inscribing everything from massive temples to tiny scarabs, with detailed texts identifying their patrons and purposes. A more troubling explanation is that the Sphinx was already ancient and mysterious by the time of the New Kingdom, its original purpose forgotten, its builder unknown, its meaning obscured by the passage of millennia. In this reading, the name Horemakhet was not the Sphinx's original name but a New Kingdom reinterpretation, an attempt by later Egyptians to incorporate an ancient and enigmatic monument into their own religious framework. The core problem, then, is this. The geological evidence, as interpreted by at least 2 independent qualified geologists, indicates that the Sphinx enclosure shows erosion that is inconsistent with the conventional 4th dynasty construction date. The counter-arguments, while serious and worthy of consideration, have not satisfactorily explained the specific features of the erosion, the vertical channels, the rounded profiles, the differential weathering depths, within the framework of the conventional timeline. The granite over eroded limestone evidence from the Sphinx temple provides independent corroboration. The silence of Old Kingdom and Middle Kingdom texts is unexplained, and yet the archaeological evidence for any pre-4th dynasty culture capable of building the Sphinx is, at present, lacking. Something is wrong with our assumptions. Either the geological evidence is being misinterpreted, and the erosion features have a cause that has not yet been identified, or the archaeological record is radically incomplete, and a culture capable of monumental construction existed in the Nile Valley thousands of years before the dynasties, leaving traces that have not yet been found or recognized. Neither option is comfortable, neither is easy. Both require us to acknowledge that something we thought we understood, either the rocks or the past, is more complicated than we believed. There is another dimension to the erosion evidence that compounds the problem: the head of the Sphinx. Look at the Sphinx carefully, in photographs or in person. Compare the condition of the head with the condition of the body. The body is severely weathered, with deep erosion channels, extensive surface loss, and large areas where the original carved surface has been completely obliterated. The head, by contrast, is in much better condition. The facial features, though damaged, are still recognizable. The Nemes headdress, the striped royal headcloth that frames the face, is still clearly defined. The proportions are still readable. The overall shape is still intact. If the head and the body were carved at the same time and exposed to the same environmental conditions for the same duration, one would expect them to show roughly comparable levels of weathering, adjusted for differences in the hardness of the rock at different levels. The difference in condition between the head and the body has 2 possible explanations. The first is that the head is carved from a harder stratum of limestone than the body, and this harder rock has resisted erosion more effectively. This is partially true. The head does sit in a geological layer that is somewhat more resistant than the layers composing the body, but the difference in rock hardness alone does not fully account for the difference in weathering. The contrast is too stark. The body has lost meters of original surface in some areas, while the head retains fine details of its carved decoration. The second explanation is that the head was recarved at a date later than the original carving of the body. If the Sphinx was originally carved with a different, larger head, perhaps a lion's head to match the lion body, and the head was later recarved into a smaller human face, then the current head surface would be younger than the body. It would have been exposed to weathering for a shorter period, explaining its better preservation. This recarving hypothesis, proposed by Schock, West and others, also accounts for another anomaly that has long puzzled observers. The head of the Sphinx is disproportionately small relative to the body. A real lion's head would be significantly larger in proportion to a body of this size. The small head could be explained if the head was reduced in size during a recarving, the sculptor removing material from a larger original to create the smaller human face. If the head was recarved, the question becomes, by whom and when? The most common suggestion is that the head was recarved during the 4th dynasty by Khafre, or one of his contemporaries, transforming an ancient lion monument into a royal portrait. This would explain the association between the Sphinx and Khafre's pyramid complex. It would explain the 4th dynasty architectural style of the nearby temples, and it would reconcile the geological evidence for an earlier body with the archaeological evidence for a 4th dynasty context. The recarving hypothesis is not proven. It is a proposal, an interpretation of the evidence that fits the available data better than some alternatives. But it has a certain elegance. It explains the differential weathering between head and body. It explains the disproportionate size of the head. It explains the association with Khafre without attributing the entire monument to him. And it explains why there is no 4th dynasty builder's inscription, because Khafre did not build the Sphinx. He modified an existing monument, recarving its head and adding the temples and causeways that linked it to his pyramid complex. There is a further piece of evidence that bears on this question. The Sphinx temple, located directly in front of the Sphinx's paws, was built from large limestone blocks quarried from the Sphinx enclosure. The geological layers in the temple blocks match the geological layers in the enclosure walls. This proves that the temple was built from rock removed during the creation of the Sphinx enclosure, and therefore that the temple and the enclosure are linked. But it does not prove that they were created at the same time. If the enclosure was carved in phases, as the seismic data suggests, then the blocks used to build the temple could have come from a later phase of quarrying, the eastern extension of the enclosure, while the original western end was carved much earlier. The Sphinx temple itself shows signs of heavy weathering that are unusual for a 4th dynasty structure. The core blocks, the large limestone blocks quarried from the enclosure, show the same rounded, water-worn surfaces as the enclosure walls. These core blocks were later faced with granite slabs, presumably during the 4th dynasty, in a style consistent with Khafre's other buildings. Some researchers have interpreted this as evidence that the temple's core blocks were already heavily weathered before the granite facing was applied, suggesting that the core blocks, and therefore the original enclosure from which they were quarried, predated the 4th dynasty by a considerable margin. The granite facing, in this interpretation, was applied by Khafre's builders to an already ancient and deteriorating structure as part of a renovation program that also included the recarving of the Sphinx's head. There is also the question of the ancient Egyptian records themselves. The dream stela of Thutmose IV, erected between the paws of the Sphinx around 1370 before the Common Era, contains a damaged inscription that may include the syllable Kaf, interpreted by some as a reference to Khafre. But the French Egyptologist Gaston Maspero, who examined the stela in the late 19th century before it sustained further damage, concluded that the inscription described Khafre as someone who cleared sand from the Sphinx, not as someone who built it. If Maspero's reading is correct, then the oldest known Egyptian text about the Sphinx describes it as a monument that was already ancient and partially buried during the 4th dynasty, a monument that Khafre restored rather than created. The so-called inventory stela found near the Great Pyramid by Auguste Mariette in the 1850s, goes even further. It describes the pharaoh Khufu, Khafre's father and the builder of the Great Pyramid, as discovering the Sphinx already in existence when he arrived at Giza. The stela is generally dated to the 26th dynasty, roughly 600 before the Common Era, and is widely dismissed by Egyptologists as a later composition that invoked Khufu's name for legitimacy. And this dismissal may be correct. But the tradition it preserves, that the Sphinx predated even the builders of the Great Pyramid, is consistent with the geological evidence and adds a textual dimension to what the rocks are saying. None of this is conclusive. None of it proves beyond doubt that the Sphinx is older than the 4th dynasty. But taken together, the erosion patterns on the body, the differential weathering depth in the enclosure, the disproportionate head, the recarving hypothesis, the weathered temple core blocks, the dream stella's possible implication that Khafre restored rather than built the Sphinx, and the inventory stella's tradition of pre-pyramidal antiquity, the cumulative weight of the evidence tilts the balance away from the conventional attribution and towards something older, something deeper, something we cannot yet fully grasp. But here's what makes this truly terrifying. The evidence is not just incomplete, it is actively disappearing. The restoration campaigns of the 1980s and 1990s covered much of the original enclosure wall surface with modern limestone blocks, making it increasingly difficult for geologists to examine the weathering patterns that are at the heart of the debate. The subsurface anomalies detected by ground-penetrating radar have never been excavated, and the Egyptian authorities have not granted permits for the kind of comprehensive interdisciplinary investigation that could resolve the controversy. The window is closing, the stones are being covered, and the questions are going unanswered. The debate over the Sphinx's erosion has not remained confined to the two opposing camps of Schoch and Lena. Over the past 3 decades, a wide range of researchers from multiple disciplines and multiple countries have examined the evidence and proposed their own interpretations. The result is a sprawling, multifaceted argument that touches on geology, climatology, hydrology, archaeology, engineering, and even politics. To make sense of it, we need to walk through the major contributions one by one, understanding what each adds to the picture and where each falls short. The first major attempt to resolve the erosion controversy after Schoch's initial presentation came from K. Lal-Gary, a geologist at the University of Louisville who had been studying the deterioration of limestone monuments for decades. Gowrie had worked extensively on the conservation of ancient stone structures, including buildings in his native India and in the Middle East, and he brought a wealth of practical experience to the question. Gowrie's position was nuanced. He agreed that the Sphinx enclosure showed significant weathering that was more severe than the weathering on nearby Old Kingdom tombs, but he attributed this difference not to rainfall from a wetter climatic period, but to the ongoing chemical interaction between limestone and moisture in the present-day environment. Gowrie argued that even in an arid climate like modern Egypt, small amounts of moisture from dew, condensation, fog, and occasional light rainfall could penetrate the surface of porous limestone and initiate a slow process of chemical dissolution. Over thousands of years, this slow but persistent process could produce significant erosion, including the rounded, flowing profiles that Schoch attributed to rainfall. Gowrie's specific mechanism focused on a process he called exfoliation weathering, in which thin layers of rock peel away from the surface as a result of differential expansion and contraction caused by temperature changes, moisture absorption, and salt crystallization. He argued that this process, operating over 4,500 years in the enclosed microclimate of the Sphinx Trench, could produce erosion features, superficially similar to rainfall weathering, without requiring a construction date earlier than the 4th dynasty. The problem with Gowrie's model, as Schoch and others have pointed out, is that it predicts erosion that should be visible on all enclosed limestone surfaces of similar age on the Giza Plateau, not just on the Sphinx enclosure. If the mechanism is the slow chemical action of dew and condensation in an enclosed space, then every enclosed rock-cut space on the plateau should show similar erosion. The Old Kingdom shaft tombs, the deep quarry cuts, and the boat pits near the Great Pyramid are all enclosed spaces that have been exposed to similar microclimate conditions for roughly the same length of time. Yet none of them shows the same type of erosion as the Sphinx enclosure. Gowry's model does not explain this selectivity. If the mechanism is universal, the result should be universal. It is not. The second major attempt to address the erosion came from the Egyptian geologist Farouk Elbaz, a prominent scientist who served as science advisor to President Anwar Sadat and who had worked extensively with NASA on the Apollo program, analyzing lunar surface photographs. Elbaz proposed that the erosion on the Sphinx could be explained by a combination of wind erosion and the action of a shallow subsurface water channel, a kind of ancient runoff channel that might have directed water toward the Sphinx enclosure during rare but intense rainstorms. In this model, the erosion was not caused by sustained rainfall over millennia, but by episodic, intense rainfall events that channeled water into the Sphinx enclosure through natural drainage pathways in the plateau surface. Elbaz's hypothesis was based on his extensive experience with remote sensing and desert geomorphology. He had studied the Sahara from satellite imagery and was familiar with the way that even hyperarid deserts can experience intense rainfall events at long intervals, events that can produce significant erosion in concentrated drainage channels while leaving surrounding surfaces relatively unaffected. He argued that such events, occurring perhaps once every few decades or centuries, could, over 4,500 years, produce significant erosion within the Sphinx enclosure without requiring a wetter climatic period. This is an interesting hypothesis, and it addresses one of the weaknesses of the conventional model by providing a mechanism for water erosion within the accepted timeframe. But it has its own problems. The drainage patterns on the Giza Plateau do not naturally direct water toward the Sphinx enclosure. The enclosure sits at a point on the plateau where runoff would more likely flow east toward the Nile floodplain than collect in the trench. Moreover, the erosion on the Sphinx enclosure walls is extensive and relatively uniform, at least in character if not in depth, rather than concentrated along specific drainage pathways. If episodic flooding were the cause, one would expect the erosion to be concentrated at the points where water entered the enclosure, with diminishing erosion further from those entry points. The relatively uniform character of the erosion suggests a more general cause, such as rainfall falling directly on the enclosure from above, rather than episodic flooding from directed runoff. The third major contribution came from the French geologist and archaeologist Jean-Philippe Lauer, who had spent his career working at Saqqara, the vast necropolis south of Giza, where the step pyramid of Djoser and dozens of other royal and private tombs are located. Lauer was a conservative voice in the debate, firmly committed to the conventional chronology. He argued that the erosion on the Sphinx enclosure was simply the result of normal desert weathering operating on a particularly soft and vulnerable section of limestone, combined with the effects of repeated burial and re-exposure that had subjected the walls to alternating cycles of moisture and desiccation. These cycles, Lauer argued, would have accelerated the chemical breakdown of the limestone, producing more pronounced erosion than would be expected from continuous exposure to a stable, arid climate. Lauer's argument has some empirical support. The Sphinx has been buried in sand and re-exposed many times throughout its history. Each burial traps moisture against the stone, and each exposure subjects the freshly uncovered surface to the drying effects of wind and sun. These cycles of wetting and drying are known to accelerate the chemical and chemical breakdown of limestone. But the argument runs into the same fundamental problem as Gowry's. If burial and re-exposure cycles are sufficient to produce the observed erosion, why do other buried and re-exposed structures on the plateau, such as the tombs and mastabas that have also been periodically covered and uncovered by sand, not show the same erosion profile? The selectivity problem remains. The Sphinx enclosure is uniquely weathered, and no explanation based on processes that should affect all structures equally has been able to account for that uniqueness. The fourth significant investigation was conducted by David Coxill, a British geologist who published a paper in the journal Antiquity in 1998. Coxill examined the Sphinx enclosure independently and concluded that the erosion features were indeed consistent with water erosion caused by rainfall, supporting Schocker's interpretation. Coxill noted that the vertical channels and rounded profiles on the Sphinx enclosure walls were indistinguishable from rainfall-induced carron, the dissolution channels found on exposed limestone surfaces in regions with significant precipitation. He argued that the features could not be satisfactorily explained by wind erosion, salt weathering, or any combination of the alternative mechanisms that had been proposed. Coxill's paper is significant because it represents an independent geological assessment that reached the same conclusion as Schock. Coxill had no connection to West, no involvement with the alternative history community, and no agenda beyond evaluating the geological evidence on its merits. His paper was published in a respected archaeological journal, lending additional academic credibility to the geological argument. The math is striking when we consider the full scope of the geological evidence. We now have at least 3 independent geologists, Schock, Reeder, and Coxill, who have examined the Sphinx enclosure and concluded that the erosion patterns are inconsistent with the conventional 4th Dynasty construction date. We have seismic data showing differential weathering depths within the enclosure. We have a clear and well-documented qualitative difference between the erosion on the Sphinx enclosure and the erosion on other Old Kingdom structures on the same plateau. And we have a climatic timeline that provides a straightforward explanation for the observed erosion, the African humid period, with its sustained rainfall, followed by a gradual drying that ended thousands of years before the conventional construction date. Against this, we have a series of alternative explanations: salt weathering, microclimate effects, episodic flooding, wetting and drying cycles, each of which addresses some aspects of the evidence, but none of which satisfactorily accounts for all of the observed features. The alternative explanations all share a common weakness. They propose mechanisms that should affect all structures on the plateau, not just the Sphinx enclosure. Yet the Sphinx enclosure is uniquely affected. This selectivity is the Achilles heel of every conventional explanation that has been proposed. But the geological evidence, however compelling, is not the only line of inquiry. The debate has also been shaped by investigations from outside the field of geology, each of which adds new dimensions to the picture. The 5th major investigation involved the astronomical alignments of the Sphinx and its relationship to the precessional cycle. Robert Bauval, working with Graham Hancock, proposed that the Sphinx was originally carved in the form of a lion, not to represent a specific pharaoh, but to represent the constellation Leo. They argued that the Sphinx was oriented to face the constellation Leo as it rose on the eastern horizon at the spring equinox. Using the phenomenon of precession, the slow wobble of the Earth's axis that causes the positions of constellations relative to the horizon to shift over a cycle of approximately 25,776 years, they calculated the date at which Leo would have risen directly in front of the Sphinx at the vernal equinox. That date was approximately 10,500 before the Common Era, a date that falls within the last ice age and predates the African humid period. The astronomical argument is elegant and has captured the popular imagination, but it faces several significant objections. First, the identification of the Sphinx with Leo assumes that the builders recognized the same constellation pattern that we use today. Constellations are cultural constructs, not natural features. Different civilizations have divided the sky differently throughout history. There is no guarantee that the people who carved the Sphinx, whenever they lived, saw a lion in the same group of stars. Second, the precessional cycle calculation tells us when Leo last rose in alignment with the Sphinx, but it does not tell us that the Sphinx was built at that time. A later civilization with knowledge of precession could have built the Sphinx to mark an earlier astronomical event. The alignment proves awareness of astronomy, not construction date. Third, the date of 10,500 before the Common Era is so early that it predates not only the African humid period, but also any known evidence of human settlement on the Giza Plateau. At that date, the last ice age was still ongoing in the Northern Hemisphere, and the climate of North Africa was very different from the conditions that would later prevail during the humid period. The sixth line of investigation examined the Sphinx from the perspective of engineering and construction technique. The British engineer and researcher Chris Wise, along with several colleagues, analysed the quarrying methods that would have been required to create the Sphinx enclosure. Their analysis focused on the volume of rock removed, the tools available in different periods of Egyptian prehistory, and the labour requirements for different quarrying techniques. They concluded that the quarrying of the Sphinx enclosure was a major engineering project that would have required significant organisational capacity, a large labour force, and sophisticated planning. These requirements are consistent with the Fourth Dynasty, which is known to have commanded exactly these resources for its pyramid building programs. But they are also consistent, in principle, with earlier periods, provided that a society with similar organizational capacity existed. The engineering analysis, like much of the evidence in this debate, is necessary but not sufficient. It tells us what was required to build the Sphinx, but not when it was built. The seventh, and perhaps most recent significant contribution, came from a pair of Ukrainian researchers, Alexander Manichev and Vyacheslav Parkhomenko, who presented a paper at a conference of the National Academy of Sciences of Ukraine. Their analysis focused on the horizontal undulations visible on the lower portions of the Sphinx's body, features that they compared to wave-cut notches found on coastal cliffs and lakeside rock formations. They proposed that these features were produced not by rainfall running down the walls from above, but by standing water rising from below, water that would have partially submerged the lower body of the Sphinx for extended periods and produced erosion similar to coastal wave action. This hypothesis implies an even more radical revision of the Sphinx's age than Schocker's rainfall model, because it would require water levels on the Giza Plateau far higher than anything documented in the historical or Holocene geological record. The last time the Giza Plateau could plausibly have been partially submerged would have been during the late Pleistocene, more than 12,000 years ago, when sea levels and Nile flood patterns were very different from today. The Manichev and Parkhomenko hypothesis has not been widely accepted, and it pushes the Sphinx's age to an extreme that most researchers, even those sympathetic to the water erosion argument, find difficult to support. But it illustrates the range of interpretations that the Sphinx's enigmatic erosion has inspired. An eighth line of inquiry, more recent and still developing, involves the application of modern analytical chemistry to the erosion products themselves. The weathering of limestone produces specific chemical byproducts, including dissolved calcium carbonate that can recrystallize within the pore spaces of the rock as secondary calcite, and clay minerals that accumulate in erosion channels as insoluble residues. These byproducts preserve information about the conditions under which they were formed, including the temperature, the isotopic composition of the water, and the chemical environment. In principle, detailed chemical analysis of the weathering products in the Sphinx enclosure erosion channels could provide independent evidence about the type and timing of the weathering process. Rainwater and groundwater have different chemical signatures. Tropical rainfall and temperate rainfall have different isotopic compositions. If the erosion channels contain weathering products that are chemically consistent with rainfall from a wetter climatic period, this would provide powerful independent support for Schocker's hypothesis. Such analyses have not been conducted, at least not to the level of detail that would be required to make a definitive contribution to the debate. The technology exists. The methods are well established in geological research, but the access has not been granted. This is another instance of the broader pattern that has characterized the Sphinx controversy. The tools to resolve the debate are available. The will to use them is not. There is also the broader climatological context to consider. The end of the African humid period was not a smooth, gradual transition from wet to dry. Paleoclimatic data from lake cores, pollen records, and isotopic analyses throughout the Saharan region suggest that the transition was punctuated by abrupt shifts, periods of rapid drying interspersed with brief returns to wetter conditions. Some of these abrupt shifts may have been triggered by large-scale climate events, such as volcanic eruptions, shifts in ocean circulation patterns, or changes in solar activity. The most dramatic of these events was the so-called 5.9 kiloyear event, a period of rapid climate deterioration around 3900 before the Common Era that may have contributed to the desiccation of the Sahara, and, some researchers have argued, to the concentration of populations along the Nile that led to the emergence of the Egyptian state. The relevance of these abrupt climate shifts to the Sphinx debate is that they complicate the simple timeline of steady drying that is often assumed. If the transition from wet to dry was punctuated rather than smooth, then periods of significant rainfall may have occurred on the Giza Plateau at dates later than the general end of the humid period, potentially bringing them closer to the conventional construction date. Some critics of Schoch's hypothesis have seized on this possibility, arguing that late-stage rainfall events could have produced the observed erosion within the conventional timeframe. But the evidence for such events on the Giza Plateau specifically, as opposed to in the broader Saharan region, is limited. And even if late rainfall events did occur, they would need to have been sustained enough and heavy enough to produce the deep vertical channels and extensive rounded erosion that are the hallmark features of the Sphinx enclosure walls. Sporadic, short-lived rainfall events are unlikely to have been sufficient. What unites all of these investigations, from Schoch's careful geological fieldwork to Bauval's astronomical calculations to Manikev's wave-cut hypothesis, is a common recognition that the Sphinx does not fit comfortably within the conventional chronological framework. Each researcher, approaching the monument from a different angle with different tools and different assumptions, has encountered evidence that does not match the standard Fourth Dynasty attribution. They disagree about the details, they disagree about the dates, they disagree about the mechanisms, but they agree, implicitly or explicitly, that the conventional story is incomplete, that the Sphinx is hiding something, that the stones know something we do not. Let us turn now to a dimension of the debate that is rarely discussed in academic papers, but that has profoundly shaped the trajectory of the controversy: the politics of access and the sociology of academic knowledge. The Sphinx is not an ordinary archaeological site. It is one of the most famous monuments on Earth, a national symbol of Egypt, and a major driver of tourism revenue. The Egyptian government, through its Ministry of Tourism and Antiquities, exercises strict control over access to the monument for research purposes. Permits for new studies, surveys, and excavations are granted selectively, and researchers who have proposed unconventional interpretations of the Sphinx's history have reported difficulty obtaining the access they need to pursue their work. Schoch himself has stated publicly that his ability to conduct additional geological surveys of the Sphinx enclosure has been limited since his initial work in the early 1990s. The subsurface anomalies detected by Dobecki's ground-penetrating radar surveys, possible voids or chambers beneath the Sphinx, have never been investigated through excavation because the Egyptian authorities have not granted permission. The original surfaces of the Sphinx enclosure walls, which bear the erosion features at the heart of the controversy, have been progressively covered by restoration blocks installed during conservation campaigns in the 1980s and 1990s, making it increasingly difficult for new researchers to examine the original rock. The result is a situation in which the key evidence is becoming less accessible over time, not more. New geological techniques, including more sophisticated forms of ground-penetrating radar, three-dimensional laser scanning, chemical analysis of weathering products, and high-resolution dating of mineral deposits within the erosion features, could potentially resolve the debate. But these techniques can only be applied if researchers are given access to the monument, and access has been, in practice, contingent on the researcher's willingness to work within the conventional framework. Those who have challenged the conventional chronology have found it more difficult to obtain permits than those who have supported it. This creates a dynamic in which the evidence needed to resolve the debate is controlled by the institutions that have the most to lose from its resolution. This is not a conspiracy. It is the normal functioning of institutional power in the academic world, amplified by the unique economic and political significance of the Sphinx. but it has had the effect of freezing the debate in place, preventing the very investigations that could move it toward resolution. And as the restoration work continues and the original surfaces are further obscured, the window for conducting those investigations narrows with each passing year. And this is where the answer becomes deeply unsettling. The erosion patterns on the Sphinx enclosure tell a story. The geologists who have examined them, including multiple independent researchers with no connection to one another, have largely agreed on what that story is. The alternative explanations offered by critics, while serious, have not been able to account for all of the observed features, and the institutional structures that control access to the monument have not facilitated the kind of rigorous, independent, interdisciplinary investigation that could resolve the debate one way or the other. We are left in a state of knowledge that is neither confirmed nor refuted, neither resolved nor abandoned. The question remains open. The stones continue to speak, and fewer people are being allowed to listen. But the debate has not stood still. Beyond the direct geological and institutional analysis, several additional lines of investigation have contributed to the broader picture, each one adding complexity and depth to a controversy that shows no signs of resolution. The comparison with Göbekli Tepe deserves extended treatment because it fundamentally alters the context in which the Sphinx erosion debate must be understood. Göbekli Tepe, located in southeastern Turkey near the ancient city of Urfa, was excavated beginning in 1995 by the German archaeologist Klaus Schmidt. The site consists of multiple circular enclosures built from large, T-shaped limestone pillars, some weighing up to 20 tons, carved with elaborate reliefs of animals and abstract symbols. Radiocarbon dating of organic material found in the fill between the pillars places the construction of the earliest enclosures at approximately 9,600 before the Common Era, making them more than 11,000 years old. Before Göbekli Tepe was discovered, the prevailing assumption in archaeology was that monumental construction required a settled agricultural society. Only farmers, with their ability to produce food surpluses and free labor from subsistence activities, could organize the collective effort needed to quarry, transport, and erect large stone structures. Hunter-gatherers, by contrast, were assumed to live in small mobile bands, without the resources or the organizational capacity for such projects. Göbekli Tepe demolished this assumption. The people who built it were, so far as the evidence indicates, pre-agricultural. They lived by hunting and gathering. They had no pottery. They had no metal tools. They had no permanent settlements, or at least none that have been found in the immediate vicinity. And yet they quarried limestone pillars weighing up to 20 tons, transported them to a hilltop site, erected them in carefully planned circular arrangements, and carved them with sophisticated relief sculptures that show a high degree of artistic skill. The implications for the Sphinx debate are profound, though indirect. Göbekli Tepe does not prove that the Sphinx is older than the Fourth Dynasty. It proves something more general, but equally important. It proves that our assumptions about what early societies were capable of are wrong. It proves that monumental construction did not require agriculture, cities, writing, or any of the other characteristics that archaeologists had long assumed were prerequisites. It proves that the deep past was more complex, more ambitious, and more capable than the surviving evidence had led us to believe. And it provides a documented, radiocarbon-dated, peer-reviewed example of a society that achieved monumental construction at a date earlier than anyone had previously thought possible. If hunter-gatherers in southeastern Turkey could build Göbekli Tepe more than 11,000 years ago, the question of whether a pre-dynastic or earlier society in the Nile Valley could have carved the Sphinx from the living bedrock becomes considerably less implausible. Not proven, not established, but less implausible. The objection that no known culture of the required period had the capacity for such a project loses much of its force when we recognize that our knowledge of what early cultures were capable of has been consistently, dramatically, and repeatedly wrong. There is also the site of Karahan Tepe, another monumental Neolithic site in southeastern Turkey discovered in recent years, roughly 35 kilometers from Göbekli Tepe. Excavations at Karahan Tepe have revealed pillared structures comparable to those at Göbekli Tepe, but with distinctive features of their own, including carved human heads and a chamber with 11 pillar-like structures arranged in a semicircle. Karahan Tepe appears to be roughly contemporary with Göbekli Tepe, dating to the 10th or 9th millennium before the Common Era. Its discovery demonstrates that Göbekli Tepe was not an isolated anomaly, but part of a broader tradition of monumental construction in the pre-pottery Neolithic of the Near East. How many other such sites remain undiscovered? How much of this tradition has been erased by time, agriculture, urbanization, and geological processes? We cannot say. But the pattern is clear. The deeper we look, the more we find. The earlier we look, the more capable the people we find appear to be. The assumptions that once seemed solid are crumbling, one by one, under the weight of new evidence. The forensic analysis of the Sphinx's face adds another layer to the debate. In 1993, Frank Domingo, a senior forensic artist with the New York City Police Department, was invited by John Anthony West to compare the facial features of the Sphinx with the known statues of Khafre. Domingo used the same measurement and comparison techniques he employed in criminal investigations, taking detailed facial proportions from both the Sphinx and the diorite Khafre statue in the Cairo Museum. His conclusion was that the two faces were significantly different and did not belong to the same individual. The proportions of the jaw, the forehead, and the overall facial structure were inconsistent. Egyptologists have responded that ancient Egyptian royal sculpture was not portraiture in the modern sense. Pharaohs were depicted according to artistic conventions that emphasized ideals of kingship rather than individual likeness. Different statues of the same pharaoh can show considerable variation. The Sphinx's face, moreover, is badly damaged, with the nose missing and the surface heavily weathered, making precise measurements unreliable. These are valid objections, but Domingo's analysis, however imperfect, adds to the accumulating body of evidence, suggesting that the conventional Khafre attribution may be incorrect. When combined with the geological evidence, the seismic data, the recarving hypothesis, and the textual traditions, the forensic analysis contributes to a picture that is increasingly difficult to reconcile with the standard narrative. The geophysical data from the Sphinx enclosure presents yet another dimension of mystery. In addition to the seismic refraction surveys conducted by Göbekli, which revealed differential weathering depths, several teams have used ground-penetrating radar to survey the bedrock beneath and around the Sphinx. A Japanese team from Waseda University, led by Sakuji Yoyum, conducted surveys in the late 1980s and reported detecting anomalies beneath the left paw and on the south side of the monument. Göbekli's own radar surveys detected what appeared to be a rectangular anomaly beneath the front paws, a feature that could represent a chamber, a tunnel, or a natural cavity in the limestone. The presence of possible subsurface voids beneath the Sphinx has been a source of intense speculation. Some researchers have proposed that these voids could be constructed chambers, perhaps containing records or artifacts from the period of the Sphinx's original construction. Others caution that the anomalies could be natural dissolution features in the limestone, which is known to contain cavities formed by groundwater over geological timescales. Without excavation, there is no way to determine the nature of the anomalies, and excavation has not been permitted. The refusal to investigate the subsurface anomalies is perhaps the most frustrating aspect of the entire Sphinx controversy. Here is a testable hypothesis. There are features beneath the Sphinx that geophysical surveys suggest may be constructed chambers. A simple excavation, conducted under proper archaeological supervision, could determine whether these features are natural or artificial, and if artificial, could provide datable materials that might help resolve the age controversy. The investigation would not damage the monument. It would not require removing or altering the Sphinx itself. It would simply involve excavating a small area beneath the paws, an area that has been excavated before in antiquity, and that is already extensively documented. And yet the investigation has not been conducted. The question has not been answered, and the evidence, whatever it might reveal, remains locked beneath the limestone, as inaccessible as the intentions of the Sphinx's original builders. We have now walked through the geological evidence in detail. We have examined the visual observations, the seismic data, the climatic timeline, and the counterarguments. We have heard from geologists, Egyptologists, engineers, and astronomers. We have considered multiple hypotheses and assessed their strengths and weaknesses. And what we are left with is not an answer. It is something more important than an answer. It is a question that refuses to go away. A question that, no matter how many times it is dismissed or deflected or buried under the weight of institutional consensus, keeps resurfacing, like the Sphinx itself emerging from the sand after yet another burial. The deeper truth of the Sphinx erosion debate is not about erosion. It is about what erosion reveals about the limits of human knowledge. It is about the gap between what we think we know and what we actually know. It is about the way that the physical world, the world of rocks and water and climate and time, can contradict the stories we tell about ourselves, and about how we respond when it does. The standard model of human civilization tells a particular story. It tells us that complex societies, civilizations with monumental architecture, writing, centralized government, and long-distance trade, first emerged in a handful of locations: Mesopotamia, Egypt, the Indus Valley, and China, between 5,000 and 6,000 years ago. Before that, the story goes, humans lived in small, relatively simple communities, farming villages, and pastoral camps that lacked the organizational capacity for large-scale construction projects. This story has been refined and elaborated over the past century and a half, supported by a vast body of archaeological evidence from sites across the globe. It is a compelling story. It is a well-documented story, and for most of the 20th century, it was an essentially unchallenged story. But the Sphinx erosion challenges it, not definitively, not conclusively, but persistently, stubbornly, with the quiet authority of stone, speaking to those who know how to listen. If the Sphinx was carved before the 4th dynasty, then there was a society in the Nile Valley capable of monumental stone carving, at a time when, according to the standard model, no such society should have existed. This does not mean the standard model is entirely wrong. It may simply be incomplete. The standard model is based on the evidence we have found, and the evidence we have found is, by the very nature of archaeological preservation, only a tiny fraction of what once existed. The model describes what we know. The Sphinx asks us to consider what we do not know, and what we do not know may be far more extensive than what we do. Let that sink in. The entire framework of human civilizational history, the timeline of development from village to city to empire, is based on surviving evidence. Surviving evidence is, by definition, the evidence that managed to persist through thousands of years of erosion, flooding, earthquakes, volcanic eruptions, sea level change, climate transformation, and human destruction. It is the evidence that was made of durable materials and deposited in favorable environments. It is the evidence that we have found in the particular locations where we have looked, using the particular techniques at our disposal. It is not all the evidence that ever existed. It is not even a representative sample. It is a biased, fragmentary, probabilistically distorted subset. And from this subset, we have constructed a narrative of human history that we treat, for practical purposes, as complete. The Sphinx erosion reminds us that this narrative may have gaps, not small gaps, not minor omissions, potentially enormous gaps, encompassing entire chapters of human achievement that have been erased by time, climate, and the perishability of the materials in which they were constructed. The pre-dynastic period of Egyptian history, the millennia before the first dynasty, lasted at least as long as the dynastic period itself, perhaps twice as long. And for most of that time, the people of the Nile Valley were building with organic materials, mud brick and reed and wood and leather, materials that decay and disappear within centuries under the conditions of the Nile Valley. Their houses are gone. Their temples, if they had temples, are gone. Their meeting places, their workshops, their granaries, their boats, all gone. What survives is what was made of stone and what was buried in desert sand. And these survivals, while invaluable, cannot tell us the whole story. They can only tell us the parts of the story that happened to involve imperishable materials in preserved contexts. Could a society capable of carving the Sphinx have existed in the Nile Valley during the pre-dynastic period, or even earlier, without leaving other identifiable traces in the archaeological record? The mainstream answer is no. The reasoning is that a society capable of organizing a monumental construction project of the Sphinx's scale would necessarily have possessed other characteristics: centralized authority, surplus production, specialized labor, long-distance trade, that would have left visible traces in the archaeological record. A society that could build the Sphinx could not have done nothing else. Its other activities, its settlements, its workshops, its cemeteries, its administrative systems would have left marks in the earth that archaeologists would recognize. This reasoning has considerable force. It is based on analogy with known civilizations, all of which left extensive archaeological footprints that included, but were not limited to, their monumental constructions. The 4th dynasty Egyptians, for example, left not only the pyramids and the Sphinx, but also an enormous quantity of pottery, stone tools, copper implements, carved reliefs, hieroglyphic inscriptions, and architectural remains at sites throughout the Nile Valley. A comparable society in an earlier period should, in principle, have left a comparable footprint. But here is the problem. The analogy assumes that earlier societies would have left the same types of traces as later ones. And that assumption may be wrong. A society that built primarily with organic materials would leave a very different archaeological footprint from one that built with stone. A society that did not use writing would leave no textual record at all. A society that occupied primarily the Nile floodplain rather than the desert margins would have had its remains buried under meters of alluvial sediment, flooded by millennia of annual inundations, and built over by every subsequent civilization that occupied the same prime agricultural land. The absence of evidence is not evidence of absence. Not when the conditions for preservation are so unfavorable, not when the search has been so geographically and methodologically constrained. The discovery of Göbekli Tepe in southeastern Turkey has provided the most dramatic illustration of this principle. Before 1995, no one suspected that a site of such monumental ambition could exist in the pre-pottery Neolithic, a period when humans in the region were hunter-gatherers, without agriculture, without pottery, without metal tools, and without any of the other characteristics that archaeologists had assumed were prerequisites for monumental construction. Göbekli Tepe shattered those assumptions. It proved that people living more than 11,000 years ago, at the very dawn of the Neolithic, could quarry, transport, and erect limestone pillars weighing up to 20 tons, carve them with elaborate relief sculptures, and organize the collective labor needed to build multiple large enclosed structures over an extended period. If Göbekli Tepe had not been discovered, its existence would have been considered impossible by mainstream archaeology. The site contradicts virtually every assumption about the capabilities of pre-agricultural societies. And yet it is there, it is real. It has been excavated, documented, radiocarbon dated, and published in peer-reviewed journals. Its existence is beyond dispute. Let that sink in. The single most important archaeological discovery of the late 20th century was a site that should not have existed according to the prevailing models of human development. What other sites might be out there waiting to be discovered that will shatter other assumptions? What other chapters of human achievement have been lost to time, buried under sediment, submerged beneath rising seas, or simply overlooked because no one thought to look in the right place? The Sphinx erosion is not proof that such chapters exist in the Nile Valley. It is a suggestion, a hint, a whisper from the stones that something does not add up, that the picture is not as complete as we thought, that the past may be deeper and stranger and more accomplished than the surviving evidence, on its own, would suggest. Consider what it would mean if the Sphinx were confirmed to be 7,000 years old. It would mean that the conventional timeline of civilizational development in the Nile Valley, the neat progression from Badarian culture to Naqada I, Naqada II, Naqada III, and finally the First Dynasty, was missing a critical chapter, a chapter in which a society existed that was capable of organizing a large labor force, managing a major quarrying operation, and executing a monumental sculpture in living bedrock, all without leaving any other trace in the archaeological record that has been recognized as such. The absence of other traces does not mean the society did not exist. It means, at most, that we have not found the other traces. They may be buried under meters of Nile alluvium. They may have been destroyed by millennia of agricultural activity. They may be hiding in plain sight, misidentified, miscategorized, or overlooked because they do not fit the expected profile. The pre-dynastic period of Egyptian history lasted at least 4,000 years, and possibly longer. For most of that time, the people of the Nile Valley built with mud brick and organic materials that have almost entirely perished. Their settlements, their workshops, their gathering places, their sacred sites, all built in perishable materials, have vanished. What survives is what was made of stone and what was placed in the ground, mostly grave goods from desert-edge cemeteries. From this thin, peripheral, preservation-biased record, we have constructed our picture of pre-dynastic Egypt, and from that picture, we have concluded that the pre-dynastic peoples of the Nile Valley were incapable of monumental construction. But what if the picture is wrong? Not entirely wrong, not in every detail, but wrong in the specific sense that it underestimates the capabilities of pre-dynastic populations because the evidence base is so profoundly incomplete. The archaeological record is not a photograph of the past. It is a heavily filtered, probabilistically distorted, preservation-biased sample of a tiny fraction of what once existed, drawing firm conclusions about what was and was not possible in the pre-dynastic period from such a sample is, at best, provisional. At worst, it is circular reasoning. We assume that pre-dynastic peoples could not build monuments because we have not found their monuments, and we dismiss the Sphinx as a possible pre-dynastic monument because pre-dynastic peoples could not build monuments. This is not science fiction. This is a legitimate geological observation made by qualified professionals that has not been satisfactorily explained within the conventional framework. The fact that it has not been satisfactorily explained does not mean it never will be. Perhaps a mechanism will be identified that accounts for the Sphinx enclosure erosion within the accepted time frame. Perhaps new evidence will come to light that confirms the Fourth Dynasty attribution beyond all reasonable doubt. Or perhaps the opposite will happen. Perhaps new evidence will emerge that supports an earlier date. Perhaps a pre-dynastic site of unexpected complexity will be discovered somewhere in the Nile Valley. Perhaps the erosion patterns will be corroborated by other types of evidence that have not yet been considered. We do not know what the future holds, but we know what the present holds. And the present holds a monument, sitting quietly on the edge of a desert plateau, whose stones are telling a story that does not match the story in the textbooks. That discrepancy, however it is ultimately resolved, is the deeper truth of the Sphinx, not the answer. The question, the recognition that the past is not as known, not as settled, not as comprehensible as we would like it to be, and the willingness to live with that uncertainty, to sit with it, to let it inform our humility about what we think we know, is perhaps the most important lesson that the Sphinx has to teach. Consider for a moment the sheer weight of what we are saying. A monument that is among the most photographed, most visited, most written about structures on the planet may be fundamentally misidentified in terms of its age and origin, not by a century or two, not by a minor calibration error in the radiocarbon dating, but by thousands of years, millennia, an entire epoch of human experience separating the real date from the assigned date. And the evidence for this mismatch is not hidden in some obscure archive or locked in some inaccessible vault. It is right there, on the enclosure walls, visible to any geologist who cares to look, photographed thousands of times, published in peer-reviewed journals, and yet the mainstream narrative remains unchanged. The textbooks have not been revised, the museum plaques have not been updated, the tour guides still say Khafre, and the rocks still say otherwise. This stalemate is itself revealing. It tells us something about the relationship between evidence and consensus, between data and narrative, between what the physical world is telling us and what the human world is willing to hear. Science is supposed to follow the evidence. When the evidence changes, the conclusions are supposed to change with it. That is the ideal. The reality, as the Sphinx debate demonstrates, is considerably more complicated. Conclusions, once established, develop their own inertia. They become embedded in institutions, in careers, in identities. They become not just beliefs, but belongings. things that people own and defend and refuse to give up, not because the evidence supports them, but because giving them up would cost too much. There is one final dimension of the deeper truth that bears mentioning. The erosion on the Sphinx is not just a clue to the past, it is a reminder of the present. The same forces that shaped the Sphinx enclosure walls, water, wind, salt, temperature, chemical reaction, are still at work today. The Sphinx is still eroding, still changing, still being shaped by forces that no human intervention can permanently arrest. The restoration blocks that cover its flanks will themselves erode in time. The concrete that fills its cracks will degrade. The drainage systems that divert groundwater will eventually fail, and the Sphinx, stripped of its modern protections, will continue the slow, patient process of returning to the bedrock from which it was carved, grain by grain, molecule by molecule, over timescales that make the entire span of human civilization look like a single breath. The erosion patterns are a message written in the only language that stone knows, the language of time. And the message is this: everything changes, everything wears away, everything, no matter how massive, how permanent, how seemingly indestructible, is subject to the patient, relentless, transformative power of water, wind, and time. The Sphinx was carved to endure, and it has endured far longer than its builders, whoever they were, could possibly have imagined. But it is not eternal, it is simply very, very patient. And its patience, like the patience of the erosion that is slowly consuming it, has a lesson for any civilization wise enough to listen. There is another dimension to this deeper truth that concerns the nature of expertise itself. The Sphinx erosion debate reveals something troubling about the way academic knowledge is constructed and defended. The erosion patterns on the Sphinx enclosure are, fundamentally, a geological phenomenon. They are features of rock that can be observed, measured, photographed, and compared with similar features on rock surfaces around the world. The people best qualified to interpret them are geologists, scientists trained in the study of rocks, minerals, and the processes that shape the Earth's surface, and the geologists who have examined the Sphinx enclosure, including Schock, Reeder, Coxill, and others, have largely agreed that the erosion is consistent with water weathering from precipitation. Yet the interpretation of these geological features has been controlled not by geologists, but by Egyptologists, scholars whose training is in languages, texts, art history, and cultural analysis. Egyptologists are experts in reading hieroglyphs, interpreting mythological texts, analyzing pottery styles, and constructing chronologies based on king lists and carbon dating. They are not trained in reading erosion patterns on limestone surfaces. They do not study the chemistry of rock dissolution or the physics of fluid flow over geological materials. When they assess the Sphinx's erosion, they are operating outside their area of expertise, however eminent they may be within their own field. This disciplinary mismatch has had profound consequences for the trajectory of the debate. Geologists present geological evidence and interpret it using geological methods. Egyptologists respond not with geological counter-evidence, but with archaeological arguments. Arguments about the absence of a pre-dynastic culture capable of building the Sphinx. Arguments about the spatial association with Khafre's pyramid complex. Arguments about the Dream Stela and the Valley Temple statue. These are valid archaeological arguments, but they do not address the geological evidence directly. They talk past it. They say, in effect, we know the Sphinx was built in the 4th dynasty because of the archaeology, regardless of what the geology says. And the geologists reply, in effect, we know the Sphinx was built before the 4th dynasty because of the geology, regardless of what the archaeology says. The result is a standoff. Two disciplines, each with genuine expertise, each with legitimate evidence, each reaching a different conclusion, and neither willing or able to engage constructively with the other's evidence. This is not how scientific disputes are supposed to be resolved. Scientific disputes are supposed to be resolved through interdisciplinary dialogue, through the integration of evidence from multiple sources, through the recognition that complex problems require complex answers, drawing on multiple areas of expertise. The Sphinx erosion debate has not followed this model. It has followed a model of territorial defense in which Each discipline guards its conclusions against intrusion from outsiders. This failure of interdisciplinary engagement is not unique to the Sphinx debate. It is a common feature of academic life, a consequence of the way universities are structured, the way careers are built, and the way funding is distributed. Specialists are rewarded for depth within their own field, not for breadth across multiple fields. Crossing disciplinary boundaries is risky, career-wise. Challenging established conclusions in a field where you are not a recognized expert is even riskier, and the result is a fragmented landscape of knowledge in which important questions that fall between disciplines, questions like the age of the Sphinx, can remain unresolved for decades, simply because no one has the authority, the incentive, or the institutional support to address them comprehensively. The Sphinx does not care about institutional incentives. It sits on its plateau, eroding quietly, bearing its enigmatic patterns, indifferent to the disputes of the tiny, short-lived creatures who cluster around its pores, with their instruments and their arguments and their theories. It has outlasted the pharaohs, the Greeks, the Romans, the Arabs, the French, the British, and the modern Egyptian state. It will outlast the current generation of Egyptologists and geologists. And the erosion patterns will still be there, still saying what they have always said, still waiting for someone to listen without preconceptions. The channels will still run vertically from top to bottom. The surfaces will still flow and undulate. The hard and soft layers will still show the telltale signature of water, not wind. And the question will still be there, unanswered, unresolved, as patient as the stone itself. What does it mean for us, the living, if the erosion patterns on the Sphinx are telling the truth? What does it change? What does it demand that we reconsider? On one level, it changes a date, a single number in a single textbook entry for a single monument. The Sphinx, instead of being approximately 4,500 years old, might be 7,000 or 9,000 or even 11,000 years old. A number shifts, a bracket moves, an entry in an encyclopedia gets revised. On this level, the change seems trivial, an academic footnote, a curiosity for specialists. But on another level, the change is seismic, because the date of the Sphinx is not just a date. It is a load-bearing pillar in the entire structure of our understanding of the human past. Move that pillar, and the structure shifts. The questions cascade. If there was a society capable of carving the Sphinx before the 4th dynasty, what else did that society do? Where did it come from? Where did it go? What other monuments did it build? What knowledge did it possess? And why has it left so few traces that we cannot even name it, cannot identify it, cannot place it in any of the categories we have constructed for understanding the deep human past? These questions are not merely academic. They touch on something fundamental about how we understand ourselves. The story of civilization is the story we tell about what we are capable of. It is the story of human achievement, of progress, of the slow accumulation of knowledge and skill and organization that has brought us from caves to cities, from flint knives to digital technology, from local bands of hunter-gatherers to a global civilization spanning every continent. The conventional timeline of this story places its beginning at roughly 5,000 to 6,000 years ago. Everything before that is prologue. Everything before that is preparation. The real story, the story of cities and writing and monuments and empires, begins in Mesopotamia and Egypt in the 4th millennium before the Common Era, and everything that follows flows from that beginning. The Sphinx erosion suggests that this beginning may not be the beginning, that the story may have earlier chapters that have been torn out and lost, that the capacity for monumental construction, and therefore the social organization and technical knowledge required to achieve it, may have existed far earlier than we currently recognize. And if that capacity existed earlier, then the entire trajectory of human development, the neat linear progression, from simple to complex, from small to large, from primitive to sophisticated, may be not so much wrong as radically oversimplified. There is a philosophical dimension here that deserves a moment of quiet reflection. We live in a civilization that prides itself on its knowledge, on its data, on its records, on its ability to document, archive, index, and retrieve information about every aspect of its own existence and the existence of the world around it. we have more knowledge at our fingertips than any previous civilization could have imagined. We have satellite imagery, ground-penetrating radar, radiocarbon dating, DNA analysis, spectroscopy, mass spectrometry, and 100 other analytical tools that would have seemed magical to the scholars of even a century ago. And yet, with all of this technology, with all of this knowledge, we cannot determine the age of a single stone monument on the outskirts of Cairo. We cannot read the erosion patterns on its walls and agree on what they mean. We cannot answer the most basic question that any visitor to the Giza Plateau might ask: who built the Sphinx and when? This failure, if it is a failure, is not a failure of technology. It is a failure of preservation. The evidence we need was carved in soft limestone, exposed to thousands of years of erosion, buried and re-exposed multiple times, covered with restoration blocks, and subjected to the chemical assault of pollution, groundwater, and climate change. The evidence is degrading. It is being lost, and we are running out of time to read it before it disappears entirely. There is a parallel here with our own civilization that is worth contemplating. We produce more data than any previous society, but we store it in media that are far less durable than stone. A hard drive lasts perhaps 10 years, a solid-state drive perhaps 20, a magnetic tape perhaps 30, an optical disc perhaps 50. Even the most optimistic estimates for digital storage lifespan fall far short of the millennia over which the Sphinx has survived. We are building a civilization of extraordinary complexity and documenting it in materials that have the permanence of smoke. The irony is bitter. The people who carved the Sphinx, whoever they were, chose a medium, limestone bedrock that has preserved their work for at least 4,500 years, and possibly much longer. The erosion patterns that are the subject of this entire debate are themselves a form of record, a geological chronicle of the environmental conditions to which the monument has been exposed over the course of its existence. Stone remembers, silicon forgets, and if our civilization were to collapse tomorrow, the monuments of ancient Egypt, including the Sphinx with its enigmatic erosion, would outlast every server, every database, every digital archive we have ever created. What would future archaeologists make of us? What would they make of a civilization that produced more information than any in history, but stored it in formats that crumbled within decades? Would they look at the ruins of our server farms the way we look at the Sphinx, with wonder and incomprehension, trying to reconstruct a world from fragments that were never designed to endure? Would they too face erosion patterns on our ruins that contradicted their assumptions about when and how we built? Would they too discover, as we are discovering now, that the past is stranger than any model can contain? There is a haunting parallel between the Sphinx's predicament and our own. The Sphinx may have been built by a civilization that has vanished so completely that we cannot even name it. Its erosion patterns may be the only testimony that civilization left behind. And if that is true, it means that an entire world of human experience, an entire society's worth of knowledge, art, belief, memory, and love, has been reduced to the language of weathered limestone. Everything else is gone. The voices are silent, the stories are lost, the names are erased. Only the stone remains, speaking in its slow, patient, geological tongue to anyone who knows how to listen. We comfort ourselves with the thought that our civilization is different, that our digital archives, our satellite imagery, our cloud storage, our global internet will preserve our memory for posterity. But the Sphinx's builders, whoever they were, almost certainly believed the same thing about their own records, whatever form those records took. They too believed they would be remembered. They too believed their achievements would endure. And they were wrong. Time proved them wrong, as time proves everyone wrong, eventually, inexorably, without exception. There is a second philosophical pause that the Sphinx demands of us. It concerns the nature of expertise and authority in the construction of knowledge. The Sphinx erosion debate is, at its core, a clash between two types of expertise. Geologists read the rock and say one thing. Egyptologists read the cultural context and say another. Both groups are qualified in their respective domains. Both are applying standard methods to real evidence, and they disagree. In a perfect world, this disagreement would be resolved through open, interdisciplinary investigation. Geologists and Egyptologists would work together, each contributing their expertise to a shared inquiry, each willing to revise their conclusions in light of the other's evidence. But in practice, the debate has been characterized more by defensiveness than by collaboration. Geologists have been told that they are not qualified to make pronouncements about archaeological chronology. Egyptologists have been told that they are not qualified to evaluate geological evidence. Each discipline has retreated into its own territory, guarding its conclusions against intrusion from outsiders. This is a problem that extends far beyond the Sphinx. It is a problem that affects every area of scholarship where complex questions require expertise from multiple disciplines: climate science, epidemiology, urban planning, artificial intelligence. All of these fields grapple with the same challenge, integrating knowledge from different domains into a coherent understanding of a complex problem. The Sphinx debate is a case study in what happens when that integration fails, when each discipline insists on its own framework and refuses to engage seriously with the evidence from other domains. When the question falls between the cracks of institutional knowledge and no one has the authority or the incentive to pick it up. The Sphinx does not care about disciplinary boundaries. It does not care about academic politics or institutional turf wars or the career consequences of challenging the conventional wisdom. It simply sits on the plateau, eroding at its own pace, bearing its enigmatic erosion patterns and waiting for someone to ask the right questions, waiting for someone to listen to what the stones are saying without filtering their testimony through the lens of what they are expected to say. And perhaps that is the deepest implication of all, that the Sphinx is testing us, not in the way the Greek myth suggests, with a riddle that has a clever answer, but in a more fundamental way. It is testing our willingness to be uncertain, our willingness to hold a question open when we desperately want to close it, our willingness to admit that we do not know, and that not knowing is not a failure, but a beginning. The erosion patterns on the Sphinx are a specific, measurable, physical phenomenon. They can be photographed, mapped, sampled, and analyzed using techniques that did not exist when Schoch first examined them in 1990. Three-dimensional laser scanning could produce millimeter-accurate models of the enclosure walls. Chemical analysis of weathering products could determine the composition and sequence of mineral deposits within the erosion channels. Isotopic analysis of calcium carbonate dissolution products could provide information about the temperature and composition of the water that caused the erosion. Optically stimulated luminescence dating, a technique that measures the time since sediment grains were last exposed to light, could potentially date the last period of significant water exposure on the enclosure walls. These techniques exist. They are used routinely in geological research around the world. They could, in principle, be applied to the Sphinx enclosure to test, confirm, or refute the rainfall erosion hypothesis with a level of precision that was not possible in the early 1990s, when Schoch conducted his original investigation. And yet they have not been applied. Not because of any technical limitation, not because of any theoretical objection, but because the institutional gatekeepers who control access to the monument have not permitted the studies to be conducted. This is not a conspiracy theory. It is a statement about the sociology of academic knowledge. Institutions protect their narratives. Narratives, once established, become invested with the authority of all the scholars who have endorsed them, all the textbooks that have printed them, all the students who have learned them. Challenging a well-established narrative is not simply a matter of presenting new evidence. It is a matter of challenging the authority of everyone who has endorsed the old narrative. An authority, once challenged, defends itself. The Sphinx erosion debate is a case study in this dynamic. The narrative that the Sphinx was built by Khafre in the 4th dynasty is endorsed by virtually every major Egyptological institution in the world. It is printed in every textbook. It is taught in every university course on ancient Egypt. It is repeated by every tour guide at the Giza Plateau. To challenge this narrative is to challenge the collective authority of an entire discipline. And disciplines, like all human institutions, are more comfortable defending their conclusions than revising them. But science, at its best, is the enterprise of revising conclusions in light of new evidence. Science advances not by confirming what we already believe, but by discovering what we did not expect. The greatest scientific breakthroughs have come not from the confirmation of existing theories, but from the discovery of anomalies, observations that did not fit the prevailing model and that forced a revision of the model to accommodate them. The erosion on the Sphinx enclosure is such an anomaly. It does not fit the prevailing model. And the question is whether the discipline that controls the narrative will have the intellectual courage to revise the model, or whether it will continue to defend the model against the evidence. The answer to that question will tell us something important, not just about the Sphinx, but about ourselves, about our capacity for intellectual honesty, about our willingness to follow the evidence wherever it leads, even when it leads to uncomfortable places, about our ability to distinguish between what we know and what we merely believe. The Sphinx has been asking these questions silently for as long as it has existed, and it will continue to ask them silently long after we are gone. There is a wall of limestone on the Giza Plateau that no one carved. It was carved by water. Not the water of the Nile, which flows reliably a few kilometers to the east, as it has flowed for longer than human memory can reach. Not the water of irrigation canals or drainage channels or artisan wells, but the water of rain. Rain that fell from a sky that is now perpetually clear, onto a plateau that is now perpetually dry, washing over stone that was freshly cut and newly exposed, working its way into the grain of the limestone, dissolving the calcium carbonate matrix, widening tiny cracks into channels, deepening channels into grooves, softening sharp edges into smooth curves, and leaving behind a record of its passage that has persisted through every subsequent age of sun and sand and silence. That record is still there. You can see it. You can touch it, if the guards permit. You can run your hand along the walls of the Sphinx enclosure and feel the shapes that water carved, the rounded undulations, the vertical grooves, the smooth, flowing surfaces that are so unlike the angular, stepped profiles left by wind and sand on every other Old Kingdom structure within sight. The record is written in stone, in the only medium that has the patience to wait for someone to read it. And it says something that the textbooks do not say. It says that the Sphinx enclosure was exposed to heavy rainfall for a sustained period of time. It says that this rainfall must have occurred during a climatic period that ended thousands of years before the conventional construction date. It says that the Sphinx may be much, much older than we have been told. This does not mean the Sphinx was built by Atlanteans. It does not mean it was built by aliens. It does not mean it was built by any of the fantastical civilizations that populate the wilder fringes of alternative history. It means, simply and precisely, that the geological evidence does not match the archaeological timeline. It means that there is a discrepancy, a mismatch, a question that has not been answered, and the proper response to an unanswered question is not denial, not dismissal, not ridicule. The proper response is investigation. Careful, rigorous, open-minded investigation, conducted by qualified professionals from all relevant disciplines, with full access to the monument and its enclosure, using the best tools and techniques available. That investigation has not been conducted, not fully, not to the standard that the question deserves. And until it is, the erosion patterns on the Sphinx enclosure walls will continue to challenge the conventional narrative, quietly, patiently, in the language of stone and water and time. We began this journey with a simple observation. The erosion on the Sphinx enclosure is different. It is different in kind, different in pattern, different in character from the erosion on every other ancient structure on the Giza Plateau. That difference is real. It is measurable. It is visible to any trained geologist who cares to look. And it has never been satisfactorily explained within the conventional chronological framework. We end this journey without a definitive answer, but perhaps that is as it should be. Perhaps the most honest thing we can say about the Sphinx is that we do not fully understand it, that we have theories and hypotheses and educated guesses, but not knowledge, not certainty, not the kind of solid, unshakable understanding that we would like to have about a monument so famous, so studied, so central to our image of the ancient world. And perhaps that is the proper response to a mystery of this depth. Not frustration, not impatience, not the demand for a neat resolution that ties up every loose end and puts every question to rest, but a kind of reverent uncertainty. A willingness to sit with the unknown and let it teach us something about the limits of our knowledge and the vastness of the past. The erosion patterns on the Sphinx enclosure are a specific, testable piece of evidence. They can be studied further. They can be analysed with techniques that did not exist 3 decades ago. They can be compared with erosion patterns on other limestone surfaces around the world, in different climates and different time periods, to build a more comprehensive understanding of what they represent. The science is not finished, the investigation is not over, the book is not closed. But even if the science never reaches a definitive conclusion, even if the debate continues for another 30 years or another 300, the erosion patterns will have served an invaluable purpose. They will have reminded us that the past is not as settled as we like to think, that the monuments we take for granted may hold secrets we have not yet imagined, that the earth records its own history in ways that human texts and human memories cannot match, and that the proper stance toward the deep past is not certainty but wonder. What we have instead is something more valuable than certainty. We have wonder. We have the recognition that the world is more complex, more mysterious, more resistant to easy explanation than we sometimes allow ourselves to believe. We have the understanding that the past is not a closed book but an open question, a landscape of unknown extent, shrouded in fog, in which every new discovery reveals not answers but better questions. And we have the Sphinx itself, sitting quietly on the edge of the desert, eroding at its own unhurried pace, bearing witness to ages that no human voice can narrate and no human text can record. The erosion patterns are a kind of writing, not the writing of scribes, with their reed pens and their ink and their careful columns of hieroglyphs, but the writing of the earth itself, composed in the slow, patient language of water on stone, a language that speaks across millennia to anyone with the training and the humility to listen. What the earth has written on the walls of the Sphinx enclosure is a single sentence, repeated in 1,000 variations across every square meter of exposed limestone. It says, "I was here. The water was here. It was here before you thought it was. It was here before the pyramids. It was here before the pharaohs. It was here before the name of Egypt was spoken by any human tongue." And the Sphinx, sitting above that writing, gazing east toward a sun that rises every morning over a world that has changed beyond recognition since the day it was carved, holds the rest of the story in a silence that no amount of scholarly debate has been able to break. It knows who carved it, it knows when, it knows the name of the civilization or the culture or the nameless community of people who saw a ridge of limestone on the edge of a plateau and decided to transform it into something that would outlast everything they knew, everything they were, everything they believed. It knows, and it is not telling. The erosion speaks, the Sphinx is silent, and between the speaking and the silence, in that narrow space where geology meets mystery and science meets the unknowable, we find ourselves, small, curious, alive for a moment on the surface of a world that has been turning for longer than we can comprehend. Looking at a monument that was old before our civilization was born, asking questions that the stones will not answer, and wondering, as every generation before us has wondered, what came before. Perhaps the next generation will find the answer. Perhaps a new technique, a new discovery, a new way of reading the stones will emerge that resolves the debate once and for all. Perhaps the Egyptian authorities will grant access for the kind of comprehensive geological survey that the monument deserves. Perhaps subsurface excavation will reveal chambers or artifacts that can be definitively dated. Perhaps a pre-dynastic site of unexpected complexity will be discovered somewhere along the Nile, confirming that the organizational capacity for monumental construction existed far earlier than currently believed. Or perhaps the mystery will endure. Perhaps the erosion patterns will continue to resist definitive interpretation. Perhaps the disciplinary divide between geology and Egyptology will persist. Perhaps the stones will keep their counsel for another 3 decades, another century, another millennium, eroding slowly, revealing nothing, waiting with a patience that no human institution can match. Either way, the Sphinx will be there, facing east, watching the sunrise, bearing the marks of water that fell from a sky that is now forever clear, and reminding every generation that encounters it that the past is deeper than we know, that the earth remembers what we have forgotten, and that the greatest monuments are not the ones we build, but the questions we have the courage to ask. The rain fell, the stone remembers, and the rest is silence, a silence that stretches from the deep past to the unknowable future, unbroken by any voice that can claim with certainty to know the truth.